This is week 10 of the upper thermodynamics course. Uh, Previous week we started with combustion and saw how a stoichiometric combustion looks and how an excess air fused and the problems with incomplete combustion, and we calculated how stoichiometric ratio and then equivalence ratios for the problem, and we try to estimate the product mole fractions, and started just started on calculating how much heat is produced in a combustion. So basically we applied the first law for the combustion process. So that's where we left the previous week, and this week we'll continue on combustion problems, and we'll do some more on the energy balance of the combustion, and also look at finding out adiabatic flame temperature and problems on those. So just like similarly we should we have any combustion process, so we try to estimate the number of moles of air which is required, or if it is given, what are the products formed and the moles of each of the products. So we do a product analysis and then try to estimate for an heat transfer. So if an inlet outlet condition is known, so we can estimate the enthalpy of the reactant and the product, and since it's a closed system, you have product reactant and product reactant coming in and product going out. So and the only energy transfer across the boundary is your heat. So if you do an first law applying to the system, you will get the enthalpy difference between your reactant and the product, which will give you the heat transfer or heat generated. So that's where we started some problems previous week. So we'll continue on those. So the first question for today is, we have octane gas. The molecular formula is C8H18 at 25 degrees Celsius and 1 atmosphere, which is entering a combustion chamber operating at steady state and burns with 120% theoretical air, which is entering at 25 degrees Celsius. So both your reactant and air are coming in at 25 degrees Celsius. So that is given. Then the combustion product exit at 1200 Kelvin and include only CO2, H2O, O2 and N2. So the rate of heat transfer from the combustion chamber to the surrounding is 2500 kilowatt. Determine the mass flow rate of the fuel in kg per second. So we know that combustion chamber, your inlet is octane gas at 25 degrees Celsius, and air which is also coming in at 25 degrees Celsius. When complete combustion, 100% theoretical air, so when complete combustion is happening, so we'll estimate the products, and then the remaining 20% air quantity in the product. So that's how we'll proceed, and we know that the combustion product is exceeding at 1200 Kelvin. So with that we can estimate the enthalpies. We can do a energy balance, and they say that we get heat transfer of 2500 kilowatt with this combustion. So we need to find out how much mass flow rate of the fuel is coming in. So this is how the process looks. So you have in the combustion chamber, you have octane coming in and then air coming in, and your product which is going out at 1200 Kelvin, and there's heat transfer of 2500 kilowatt to the surrounding. So denoted by minus sign, so to denote that your to the general sign convention is for us mechanical engineers, we see that heat we are gaining is an positive quantity, and then work delivered is a positive quantity in terms of an engine. So similarly here at minus 2500, as it is just reversed to show that it is coming in. So minus 2500 is coming in, so that means 2500 kilowatt is going out. So to start with, we'll estimate for 100% theoretical or stoichiometric balance how the complete combustion equation will be like this. We have take 1 mole of C8H18 and we'll take some A moles of air, O2 plus 3.76 N2, and then it will form, for complete combustion, it will form CO2 H2O and there will be N2. So we have B, C and D. So we'll do each of the species balance just like we did in the previous week. So we'll do, and we'll find out the each of the coefficient for the equation. So we'll get 1 mole of octane will react with 12.5 moles of air, so which is oxygen plus 3.76 moles of nitrogen, to form 8 moles of CO2, then 9 moles of water H2O plus 47 moles of nitrogen. So this is for 100% theoretical air, we need to use 120%. So we will multiply 12.5 with 1.2 to make it 120%. So 1 mole of C8H18 plus 1.2 times 12.5 will give, so A CO2, B H2O plus CO2 plus DN2. So A and B will remain same. There will be, because it goes again as a complete combustion, so we will have the same number of CO2 and H2O. So we will have excess O2, which is 0.2 times 12.5. So we'll get 2.5 into 12.5 into 3.76 as D, which is 56.4. So this is how the expression chemical equation looks for combustion with 120% theoretical air. So we'll have 1 mole of C8H18 reacting with 15 moles of air, O2 plus 3.76 moles of nitrogen. So gives 8 moles of CO2, 9 moles of water, and then 2.5 moles of oxygen plus 56.4 moles of nitrogen. So with this we know the combustion equation. Next we will do an energy balance. So what is known? We know the inlet. Now we know what is the inlet and what is the product, the quantities, and then we also know the temperature of the reactant and product. So if we do an energy balance across the combustion chamber, so enthalpy in minus reactant equals Q rearranging, we will get Q mass of fuel, sorry, mole of fuel into H enthalpy of product minus enthalpy of reactant. So enthalpy of reactant can be expressed as enthalpy of formation, so this will be at some temperature, and plus you have the change in, because your product is coming in at 1200 Kelvin, so there will be enthalpy change from your formation temperature to your temperature at the product. So Just a second, my system is not responding. So as I told, we have reactant and product, and reactant formation temperatures will be different from the temperature at which the product or the reactant is coming in or going out. So we take at the enthalpy formation plus the delta H, the enthalpy because of the temperature rise. So that's why enthalpy of formation plus delta H for the octane, and then similarly for oxygen and nitrogen multiplied by, similarly for product we have 8 moles of CO2, enthalpy formation of CO2 plus delta H of CO2, and 9 moles of into enthalpy of formation plus delta H of water, and for oxygen and nitrogen. Since enthalpy formation of air, oxygen and nitrogen are 0 and at 25 degrees Celsius, so this will become, everything will become 0 for in the reactant, and enthalpy formation is 0 for oxygen and nitrogen in the products. And then substituting the values for enthalpy formation and delta H from the tables, for in the reactant will be 208 450 kilojoule per kilomole for octane. And similarly, substituting the enthalpy of formation value and enthalpy change value for the other product for components. So in substituting the values here, we'll get enthalpy of product as minus 2998680 kilojoule per kilomole of octane. And since we know is the mole of fuel equals your Q of C, heat which is following the transfer from the control volume, equals your number of moles of fuel into enthalpy of product minus enthalpy of reactant. So QCV is given as minus 2500 kilowatt, divided by substituting the enthalpy values for the product and reactant, we will get 8.96 into 10 power minus 4 kilomole of octane per second. So that is the flow rate. So we need to find it in terms of mass flow rate, because the problem asks to find the mass flow rate of fuel in kg per second. So to find the mass of fuel is nothing but multiply by molar mass of the fuel. So see 8 H18, so 8 into 12 plus 18 into 1, we get 114. So 114.22 is the molar mass, in multiply by the number of mole flow rate. So we get 8.96 10 power 4 minus 4 will give you 0.102 kg of octane per second. So that is the flow rate for octane to produce 2500 kilowatts of heat. So next is a similar problem. We have liquid propane which from 5 degrees Celsius and 1 atmosphere enters a well insulated reactor operating at steady state, same temperature and pressure. For liquid propane, enthalpy of formation is minus 900 kilojoule per kilomole. Determine the temperature of the combustion products in Kelvin with the theoretical amount of air, and then 300%. So just like octane, here we have propane coming in at 25 degrees Celsius atmosphere, and we know the enthalpy formation of. We need to find out the products for complete combustion and at what temperature the products are coming out. So for complete combustion with theoretical amount of air, we have propane which we are reacting with some amount of moles of air. So A into O2 plus 3.76 nitrogen gives you BCO2 plus 4 DH2O plus nitrogen. So if you do each of the component balance, this is the expression which you will get. So propane plus 5 moles of oxygen plus 3.76 into 5 moles of nitrogen reacts to form 3 moles of carbon dioxide, 4 moles of water and 18.8 moles of nitrogen. So for complete combustion with theoretical air, so we have to multiply with the theoretical air constant. So this is how the expression will look. So propane plus 5 into n times the amount of theoretical air. So O2 plus 3.76 N2 will give you 3 CO2 plus 4 H2O plus 5 into n minus 1 O2 plus 18.8 into n times nitrogen. So if you do an energy balance, since this combustion chamber is fully insulated, previously we had a heat transfer, here is fully insulated, so Q will be 0. So enthalpy of product will be equal to enthalpy of reactant in this case. So the enthalpy of product and reactant we have to find. So we know the product components, and reactant is your propane, and oxygen and nitrogen are coming in at 25 degrees Celsius, so their enthalpy will be 0. So substituting, we have enthalpy formation of propane plus delta H will be 0, since this is coming at 25 degrees Celsius, and similarly for oxygen and nitrogen it's 0, minus enthalpy of product, so mole into the enthalpy, so enthalpy formation of CO2 plus enthalpy of CO2 of the product minus enthalpy of CO2 at 298, basically delta H. So similarly for water and oxygen and nitrogen, so this is how the expression will look. So rearranging, we get 3 times enthalpy of CO2 plus 4 times enthalpy of water plus 5 into n minus 1 enthalpy of oxygen plus 18.8 into enthalpy of nitrogen at this all at product temperature equals enthalpy of formations. So substituting the enthalpy of formation in the equation, so we will get enthalpies of products at product equals 206387 times n plus 2053238. So that is the expression, final expression. So for 100% theoretical air, n is 1, and in this case we need to find out the as we will start with some temperature value, and we will estimate the enthalpies corresponding to that temperature, and we will substitute here and find whether the left hand side and right hand sides are equal. If not, if the enthalpy on the left side is lower, then we will proceed with a higher enthalpy value, sorry, higher temperature value, and iteratively we will try to find a temperature which will satisfy this equation. So for n equals to 1, that is 100% theoretical air, 2380 Kelvin is the product temperature when this will be equal to the enthalpy of the reactant. And similarly for n equals to 3, your product temperature will be 1150 Kelvin. So if you see here, since we are using 200% more theoretical air, and that energy is not being utilized anywhere, it just goes in heating up oxygen and nitrogen. So much of the energy which has been generated in the combustion has gone into heating the oxygen and nitrogen to the product temperature. So that's why when we are using higher theoretical air, your product temperature has decreased. Initially it was at 2380 Kelvin when we are using just complete combustion and no excess of oxygen or excess air is used. So that's the temperature, but adding excess air has reduced your product temperature. So moving on to next question, we have ethane which is burned with stoichiometric amount of air. The heat transfer is to be determined if both the reactants and products are at 25 degrees Celsius. Both, so in this case, previously the product temperature were at different temperature compared to the reactant temperature. So reactant were at your ambient 25 and 1 atmosphere. Here again, here both reactant and product are at 25 degrees Celsius. So ethane is combusting with stoichiometric air, so it gives a complete combustion, so 100% theoretical air. So you have ethane. So the combustion equation looks like 1 moles of ethane requires 3.5 moles of air, so O2 plus 3.76 nitrogen, to combust and form 2 moles of CO2, 3 moles of water and 13.16 moles of nitrogen. So now since both are at 25 degrees Celsius, which is the standard reference state, and enthalpy of formation for nitrogen and oxygen at this temperature is 0. So the final expression will look like Q is enthalpy of product minus enthalpy of reactant. So enthalpy of product is your mole into enthalpy of formation of CO2 plus delta H will be 0 because both are at standard reference temperatures. So enthalpy of formation of CO2 plus moles into enthalpy of formation of water, and nitrogen will be 0. So minus enthalpy of reactant, which is mole into enthalpy of formation of ethane. Now substituting the enthalpy of formation values for CO2, water and ethane. So CO2 is 393520 kilojoule per kilomole and 241820 for water and 884,680 for ethane. So substituting, we get 2 into enthalpy formation of CO2 and then 3 into enthalpy formation of water minus 1 into enthalpy formation of ethane. So we get Qs minus 1427820 kilojoule per kilomole of ethane. So that's the amount of heat which is received from combusting ethane. So next is ethane is burnt with stoichiometric amount of air at 1 atmosphere and 25 degrees Celsius. The minimum pressure of the product, which will assure that the water in the products will be in vapor form, is to be determined. So we need to find out the pressure at which the water will not condense. So we will have the same similar expression in the just like the previous problem. So we found out for complete combustion of ethane, so we will have 1 mole of ethane burning with 3.5 moles of air to give 2 moles of CO2, 3 moles of water and 13.16 moles of nitrogen. So at minimum pressure, the product mixture will be saturated with water vapor. So P sat at 25 degrees Celsius is, that's the partial pressure of water vapor, is 3.1698 kilopascal. So the mole fraction of water in the product is your number of moles of oxygen, water divided by the total number of moles in the product. So here we have 3 moles of water, and the total number of moles of product is 2 plus 3 plus 13.16. So we'll have mole fraction as 3 divided by 2 plus 3 plus 13.16, which is 18.16. So we'll give you mole fraction of water as 0.1652 for water. So from partials, Dalton's partial pressure law, we have your total pressure of the product, which will be the minimum pressure, is partial pressure of water vapor divided by your mole fraction. So this will give you a pressure as 19.2 kilopascal. So if your pressure is lower than this, water will start condensing. So this is the minimum pressure which you will require, such that the water will stay as a vapor. So that's why we started with calculating. We know that your product is going out at 25 degrees Celsius. So we estimated what is the saturated pressure corresponding to this 25 degrees Celsius, and that is your partial pressure of the water vapor present in the product. And at this condition, it should be saturated. If any lower, it will start condensing. So moving on, the next question: the higher and lower heating values of liquid propane are to be determined and compared to the listed value. The molar masses of carbon, oxygen, hydrogen and air are 12, 32, 2 and 29 kg per kilomole respectively. So we need to find out the heating value for propane. So propane in liquid form reacts with 5 moles of air to form 3 moles of CO2, 4 moles of water and 18.8 moles of nitrogen. So this is the combustion equation for propane. So now both the reactant and product are at standard reference temperature and pressure. So we just like the previous, there will be no enthalpy change because both are at 25 degrees Celsius. It's just enthalpy of formations. So Q is enthalpy of product minus enthalpy of reactant, and enthalpy of product is nothing but summation of number of moles into enthalpy of the product component minus enthalpy of reactant into the mole of that reactant. So this is how the expression will look like. Since nitrogen and oxygen have enthalpy of formation of 0, the equation will reduce to Q equals to N into enthalpy of formation of CO2 plus mole of water into enthalpy of formation of water minus mole of propane into enthalpy of formation of propane. So the enthalpy of liquid propane is obtained by adding HFG to of propane at 25 degrees Celsius to enthalpy of gas. So we'll get enthalpy of liquid as 118,620 kilojoule per kilomole. So we get, here we have multiplied by, so if you see molar mass of propane, which is 3 into 12 is 36 plus 8 which is 44. So we have enthalpy of formation of gas propane is 103,850 plus we multiply molar mass into 335 because 335 in kilojoule per kg. So to convert it, we are multiplying by molar mass. So we get 118,620 kilojoule per kilomole. So this was also given in the previous problem. So next we need to find out the HHV higher heating value. In this case, the water of the product, the water in the product will be considered to be in liquid form. So we need to consider the latent heat of water in the heat which is transferred. So what we'll get, so Q is here enthalpy because of combustion, we'll get 3 into minus 393,520, this is for CO2, then 4 into minus 285,830, it's for water, and then minus 1 because we have taken 1 mole of the fuel, into minus 118,620 kilojoule per kilomole. So we get minus 2,205,260 kilojoule per kilomole. So the higher heating value of the liquid propane is HHV is Q by your molar mass, so it gives you 50,010 kilojoule per kg. So if you see, the listed value is 50,230 kilojoule per kg. So this is close to the listed value. Next is we need to find out the lower heating value. So in the case of lower heating value, we consider the water as a gaseous form or in vapor form. In that case, your again the difference in enthalpy formation is just the latent heat. So this is in the enthalpy formation for is in liquid form, and here it's in vapor. So we have to just add and enthalpy of latent heat to enthalpy formation of liquid. So we will get enthalpy formation for vapor for water. So in this case, again the other values will be same, only the enthalpy formation of water will change. Or we can just straight away add HHV equals HHV plus your latent heat to find out LHV. So LHV of propane is then substituting the value minus Hc by molar mass. So we'll get 46,020 kilojoule per kg. So listed value is 46,340. So if you see, the LHV will always be lower than HHV because here the water is in vapor form. So if you extract some more heat, the water will condense, and that's why you get higher heating value. So HHV will be higher, that's why higher and then lower. So next question, we have calculated the higher and lower heating values for a coal from Illinois, which has an ultimate analysis by mass as 67.4% of carbon, 5.31% of hydrogen, 15.11% of oxygen, 1.44% of nitrogen, 2.36% of sulfur, and 8.38% ash. So the enthalpy of formation of sulfur dioxide is 297,100 kilojoule per kilomole. So for this we'll estimate. So first is they have given in terms of mass for the coal. So the mole of carbon is mass fraction of carbon is your mass of carbon divided by the total mass. Sorry, we are estimating the mole. So mole of carbon is mass divided by molar mass. So mass of carbon is 67.4 divided by 12 kg per kilomole. So we get 5.617 kilomole. And similarly, hydrogen is mass of hydrogen divided by molar mass of hydrogen. So we get 2.655 kilomole. And then mole of oxygen is mass of oxygen divided by molar mass of oxygen, is 15.11 kg divided by 32 kg per kilomole. So which gives you 0.4722 kilomole. Then we have mole of nitrogen, and similarly you get 0.05143 kilomole, and mole of sulfur as 0.07375 kilomole. So the total mole of the mixture is when you add up all the moles, you get 8.869 kilomole. Next is we find out the mole fraction for each of the component. So C is mole of carbon divided by total mole, you get 0.633. Then hydrogen is 0.2944, and oxygen is 0.05323, and nitrogen is 0.00580, and sulfur is 0.00832. So these are the mole fraction for each of the component. So what we since we write combustion equation in moles, so we estimate the moles, and from there we found out the mole fractions to know what is the fuel. So this is the fuel. One mole contains each of this component in this mole quantities. Then that is reacted with some A for complete combustion, theoretical air, 100% theoretical air. So A into O2 plus 3.76 nitrogen to form X moles of CO2 and Y moles of water plus Z moles of SO2 plus K moles of nitrogen. So here they said some quantity of ash is present. Since that is not taking part in combustion, we are neglecting that, because whatever mass is coming in, it will go out. So we are neglecting that part for simplicity here. So next is we'll do a species balance for each of the species to find out the unknowns. So first starting with carbon. So X is 0.633. Then we'll do hydrogen balance, which will give Y as 0.2994. Then sulfur balance, Z as 0.00832. Next, doing an oxygen balance, we'll get A as 0.7381. Then nitrogen balance will give you 2.781. Substituting this, how the expression looks: 0.6333 is carbon plus 0.2994 hydrogen. So this is fuel plus 0.7381 of air combust to form these products. So when we do again, we assume that both reactant and product are coming in and going out at the standard reference temperature and pressure, which is 25 degrees Celsius and 1 atmosphere, because we need to calculate the heating value. So we, in that case, we will assume both reactant and product are at standard reference and temperature. In this case, if you see, carbon, sulfur, hydrogen, nitrogen and oxygen are stable element and their enthalpy of formation is 0. So if you do first law, so Q is enthalpy of product minus enthalpy of reactant. So writing the expression, we will get number of moles of CO2 into enthalpy of formation of CO2 plus number of moles of water into enthalpy of formation of water plus number of moles of sulfur dioxide into enthalpy of formation of sulfur dioxide. The rest will all be 0. So substituting the enthalpy formation and the moles of CO2, water and SO2, we get for combustion is minus 3,37,270 kilojoule per kilomole for per mole of coal, per kilomole of coal. So this much amount of energy is released. So this equals to the higher heating value. So here the enthalpy formation of water is taken as liquid. Next is we find the molecular weight of the coal, that is nothing but mass divided by your mole. So since we know the mass fraction into molar mass of each of the component, so we get 0.633 is the mole of carbon into your molar mass of carbon, plus that will give you the mass of your carbon will present. So similarly we do it for other component, divided by the total number of moles, which will give you the molar mass. So we get 10.33 kgs of the coal divided by 1 kilomole. So your molar mass is 10.33 kg per kilomole of coal. So the higher heating value is in terms of kilojoule per kg. So we divide it by the molar mass to give 32,650 kilojoule per kg of coal. Similarly, for lower heating value, we consider the water to be in vapor form. So we substitute the enthalpy of formation of water in as vapor. So in that case we get Qs minus 3,24,090 kilojoule per kilomole, and similarly we divide it by the molar mass, which gives you lower heating value as 31,370 kilojoule per kg of coal. So here if you see enthalpy formation of table, here both the values are listed. So water, if you consider, both gaseous and liquid values are already given here. So we have to just plug in those values. And similarly for some other components, here propane only in gas was given. So we added the enthalpy of latent heat, so minus 103 900, so minus your enthalpy of latent heat enthalpy, so that will give you liquid. It is just nothing but enthalpy of gas is enthalpy of liquid plus your latent heat. So that's what just wanted to show you that. So we have found out latent heat lower heating value. So next question is, we have propane fuel pressure heating furnace, we need to determine the heat transfer per kilogram of fuel burned when the temperature of the product is such that liquid water just begins to form in the product. So, they have given air fuel ratio is given, which is 25, and it is in atmospheric pressure heating furnace. So, pressure in atmosphere, you need to determine heat transfer per kilogram of fuel burnt such that the temperature of the product is such that liquid water will start forming. So, it has reached its dew point. So, we will see how to solve this. So, since air fuel ratio is given, air fuel ratio is nothing but your mass of air divided by mass of fuel. Air fuel ratio is given as 25 kg of air per kg of fuel. So, if you consider 1 mole of fuel, there is 1 mole of propane. So, propane molar mass is 44. So, the mass of fuel is 1 into 44, that is mole into molar mass is your mass. So, that into 25 will give you 1100 kg of air per kilomole of fuel. So, the mole number of air per kilomole of fuel is then your mass of air divided by your molar mass of air. So, you are using 1100 kg of air for the combustion of 1 mole of fuel. So, 1100 divided by 29 will give you 37.93 kilomole of air. So, that is the mole of air which is used for combustion. So, your expression will be 1 mole of propane. Here we are assuming air. So, air contains 4.76 moles totally. So, we have 1 oxygen and nitrogen. So, we have to divide this by 4.76. So, you have 1 mole of propane reacting with 37.93 divided by 4.76 times oxygen plus 3.76 into nitrogen to form 3 CO2 plus 4 H2O plus XHO2 plus 37.93 divided by 4.76 into 3.76 nitrogen. So, you need to find out X. So, doing an oxygen balance, we will get X as 2.968. So, substituting this the final expression, we have C3H8 plus 7.968 O2 plus 3.76 N2 gives you 3 moles of CO2 plus 4 moles of water plus 2.968 moles of oxygen plus 29.96 moles of nitrogen. So, with this we need to find out the mole fraction of oxygen, water, because we need to find out the partial pressure, and with that we can find out the temperature which is required for it to start condensing. That is the saturated temperature corresponding to that pressure. So, for that we will first find out the mole fraction. So, mole fraction of water vapor is your number of moles of water divided by the total number of moles in the product. So, you have 4 moles of water. So, 4 divided by the total moles, that is 3 plus 4 plus 2.968 plus 29.96, which is 39.93. So, your mole fraction is 4 divided by 39.93, giving you 0.1002. So, that is the mole fraction for water. Then your partial pressure of water will be mole fraction into total pressure. Since they have given it is atmospheric pressure heating furnace, your product will also be in atmospheric pressure. So, mole fraction into atmospheric pressure. So, 0.1002 into 101.325 kilopascal. So, that will give you 10.15 kilopascal. So, the dew point temperature corresponding to this pressure is 46.1 degrees Celsius or 319.1 Kelvin. So, approximately 320 Kelvin. So, this is the temperature at which your product should exit for it to be a condition at which water can start forming as a liquid. So, we get the enthalpy values corresponding to 320 Kelvin. So, we do an energy balance across the combustion chamber, your Q is enthalpy of product minus enthalpy of reactant, just like the previous. So the enthalpy formation values are given here, and similarly enthalpy at the standard temperature 298 Kelvin and at 320 Kelvin is listed in the table below. So I have to just substitute the values. So here again the enthalpy formation for oxygen and nitrogen will be 0. So the final expression will be your number of moles into enthalpy formation of CO2 plus delta H of CO2. Similarly, in number of moles of water plus enthalpy formation of water plus delta H of water, that is enthalpy at your product temperature minus enthalpy at 25 degrees Celsius or 298 Kelvin, and then enthalpy change number of moles of oxygen into delta H of oxygen, and similarly number of moles of nitrogen into delta H of nitrogen minus your enthalpy formation of propane into number of moles of propane, that is 1. So that's how the expression will look like, and substituting the values you get Q out as minus 2017590 kilojoule per kilomole of propane. So Q out is we get 20,17,590 kilojoule per kilomole. So to convert it into per kg, we divide it by your molar mass. So divided by 44 will give you 45,850 kilojoule per kg of propane. So next question is, we have hydrogen which is burnt completely with the stoichiometric amount of air during a steady flow combustion process. If both the reactants and the products are maintained at 25 degrees Celsius and 1 atmosphere, and the water in the products exit in the liquid form, determine the heat transfer from the combustion chamber during this process. What would your answer be if combustion were achieved with 50% excess air? So first we will write a combustion equation for hydrogen for complete combustion. So hydrogen reacts with some A into moles of oxygen and 3.76 moles of nitrogen to give water plus 3.76 into A moles of nitrogen. So A will be nothing but 0.5. So you get H2, 1 mole of hydrogen reacts with H2 reacts with 0.5 moles of O2 plus 3.7692 to give H2O plus 1.88 nitrogen. So the enthalpy formation for the components, since enthalpy of formation for hydrogen, oxygen, nitrogen being stable molecules will be 0. So that's listed, and enthalpy of water, formation of water at as liquid is minus 285830. So substituting the values, so Q will be nothing but you adjust number of moles of water into enthalpy formation of water. Since both reactant and product are coming at standard temperature and pressure, so there is no delta H, so that all be 0, and reactants is 0, enthalpy is 0, and product nitrogen is 0. So just water is there, so Q will be nothing but the enthalpy formation of water into moles, that is also 1. So Q out is 285,830 kilojoule per kilomole. So if you want to convert into per kg, divide by molar mass, which is by 2. So then you will get 1,42,4 0.429115 kilojoule per kg of hydrogen. So next part of the question was, when it reacts with 50% excess air, how much will be the heat generated? So what would the answer be if combustion was achieved at 50% excess air? In that case, how much heat transfer will happen? So since again the product is even though excess air is used, the product is coming out at 25 degrees Celsius. So whatever energy would have absorbed by the excess air will be released when it is brought back to 25 degrees Celsius. So your heat transfer will remain same. So it will not vary. So it will vary only when your product is at a different temperature. Then the product, because the air which is coming in at 25 degrees Celsius has to rise to the product temperature. So it will take away some amount of heat which is generated. So in that case, whatever heat is transferred across the combustion chamber outside the boundary will reduce. Here both the product and the reactant are at 25 degrees Celsius. So even though during the combustion it would have increased, when it will release that heat while coming back to 25 degrees Celsius. So your heat will not change. So Q out will remain same as 285830 kilojoule per kilomole. So moving on to the next question. We have gaseous E10 fuel is 10% ethanol and 90% octane on a kilomole basis. So this fuel is burnt with 110% theoretical air. So during the combustion process, 90% of the carbon in the fuel is converted to CO2 and 10% is converted to CO. Determine the balanced combustion equation, be the dew point temperature of the product in degree Celsius, this is degree Celsius, for a product pressure of 100 kilopascal. The heat transfer for the process in kilojoule after 2.5 kg of fuel are burnt and the reactants and products are at 25 degrees Celsius with water in the products remaining a gas, and relative humidity of atmospheric air for the case where the atmospheric air is at 25 degrees Celsius and 100 kilopascal, and the products are found to contain 9.57 kilomole of water vapor per kilomole of fuel burnt. So we'll see how to solve this. So first we'll write the balanced combustion equation for 10% ethanol and 90% octane. On kilomole basis. So this is all written in molar basis, so we can write directly. So if we contain 1 mole of 1 kilomole of fuel, it will contain 0.1 kilomole of ethanol and 0.9 kilomole of octane. So that's what is written: 0.1 mole of ethanol plus 0.9 moles of octane plus A reacting with air, O2 plus 3.76 nitrogen to form. They are given 90% of the total carbon. 90% of the carbon is in the fuel is converted to CO2. So here we have 10 . So first we'll find out how much moles of carbon dioxide is present. So from there we know how much CO and CO2 is forming. So first we'll write a complete combustion equation. So we'll have 0.1 kilomoles of ethanol plus 0.9 moles of octane reacting with A moles of air to form. So doing a balance, carbon balance, we'll get 7.4 moles of CO2 plus 8.4 moles of water plus A mole into 3.76 moles of nitrogen. So from there we can find out A to come out to be 11.55. So substituting, this is the final expression. Now we are reacting with 10% excess air, and we are saying that 90% is converting into CO2 and rest is forming as CO. So we have 7.4 moles of CO2, so out of which 90% is now converted to CO2. So we have 0.9 into 7.4 CO2 plus 0.1 into 7.4 CO, and the water will remain same, and we have excess oxygen and nitrogen. So now estimating the moles of oxygen, we get oxygen as 1.525 moles. So this is the final expression, final balanced equation for the incomplete combustion, which is given in the problem. So we have 0.1 moles of ethanol plus 0.9 moles of octane reacting with 12.705 moles of air to form 6.66 moles of CO2, 0.74 moles of CO plus 8.4 moles of water and 1.525 moles of oxygen to form 47.77 moles of nitrogen. So the partial pressure of water vapor is your mole fraction into your total pressure. So mole fraction is your number of moles of oxygen divided by number of moles, total moles. So number of moles of oxygen is 8.4 divided by the total moles, which is 6.66 plus 0.74 plus 8.4 plus 1.525 plus 47.77 into your total pressure is 100 kilopascal. So it will give you partial pressure of water vapor as 12.9 kilopascal. The corresponding saturation pressure to this saturation pressure, your temperature is 50.5 degrees Celsius. So we know the dew point temperature, which has been asked. Next is we need to find out the heat transfer or the heating value. In this we are asking the water in the product remaining as gas, so we have to find out the LHV. So Q is nothing but your enthalpy of product minus enthalpy of reactant. So since both reactant and product will be leaving at 25 degrees Celsius, so substituting the values are similar to what we did in the previous problem, we will get Q as 45 lakh to 22,790 kilojoule per kilomole of fuel. So if you consider the molar mass, so we have 0.1 into 46 for ethanol and 0.9 into 114 for octane to form, so the molar mass of the combined fuel is 107.2 kg per kilomole. So we will divide it on the with Q. Into your mass for 2.5 kg of fuel, which is given in the problem for 2.5 kg of fuel. So 2.5 into Q out divided by molar mass. So we will get 1,05,480 kilojoule. That is the heat which is transferred. Next, we need to find out the relative humidity when 9.57 kilomole of water vapor is there in the product. So we know from the balanced expression here that water quantity is 8.4 moles of water has been formed. So the rest excess water is what is present in the air. So the problem states that we have 9.57 kilomole of water vapor in the air. So the remaining kilomole of water vapor should be present in air. So 9.57 minus 8.4 gives you 1.17 kilomole. So this is the kilomole of water vapor which is present in atmospheric air. So the partial pressure of this water vapor in this atmospheric air is 1.17 divided by your 12.705, which is the mole of air in the expression. If you see here, balance 12.705 moles of air being used for combustion. So 12.705 into 4.76, because 1 mole of air contains total 4.76 moles of oxygen and nitrogen. So 12.705 into 4.76 plus mole of water, that will give you the mole fraction of water into your total pressure. So your partial pressure is 1.8979 kilopascal. So the saturation pressure for water at 25 degrees Celsius is 3.17 kilopascal. So we know relative humidity is nothing but your partial pressure of water vapor divided by your saturation pressure. So that is 1.8979 divided by 3.17, which will give you 59.9%. So that is the relative humidity of the air which has to be used for water at the product to be 9.57 kilomole. So next is compare the adiabatic flame temperature of propane fuel when it is burnt with stoichiometric amount of air and when it is burnt with 20% excess air. So the reactants are at 25 degrees Celsius and 1 atmosphere. So again here it is 25 degrees Celsius and 1 atmosphere. So two cases, when excess air is used, what is the adiabatic flame temperature, and when stoichiometric air and 20% excess air. So how the adiabatic flame temperature is varying. So since it's an adiabatic flame temperature, so you have an adiabatic process, there is no heat transfer. So what is the temperature of the product? So your enthalpy of product will be equal to enthalpy of reactant in this case, since Q is 0, W is 0, there is no heat and work transfer. So first we will write the combustion equation. So you have 1 mole of propane reacting with A moles of air to form 3 moles of CO2 plus 4 moles of water plus A into 3.76 moles of nitrogen. So AL comes out to be 5. So the final expression will look like 1 mole of propane react with 5 moles of air to give 3 moles of CO2, 4 moles of water and 18.8 moles of nitrogen. So the enthalpy formation and the enthalpy at 25 degrees Celsius is given. So the expression will look like this. So the enthalpy formation, number of moles of CO2 equals the enthalpy formation of CO2 plus enthalpy of CO2 at the product temperature or the adiabatic flame temperature minus at enthalpy at 25 degrees Celsius. Similarly, enthalpy for water and nitrogen, enthalpy formation of nitrogen will be 0, and similarly for oxygen equals number of moles of your fuel into enthalpy formation of fuel. So which will give you 3 moles of enthalpy of CO2 at adiabatic flame temperature and 4 moles of at water at enthalpy of water at adiabatic flame temperature, and similarly for nitrogen equals 22,74,680 kilojoule. So now we'll start with an initial guess. So we can start with 2650. So substituting starting with 2500. So we substitute the enthalpy values corresponding to 2500 Kelvin, and substituting we find that the enthalpy value we get is more than what is there on the right hand side. So we reduce it a little bit. So next iteration we take it at 2450. Then we find it's still higher, we get 23,034 990 instead of 22,074 680. Then we reduce the temperature again, and still it is a little bit higher compared to the required value at 2350. These two, it will find, you can find. So pressure, your temperature is 2121 degrees Celsius is your adiabatic flame temperature. And similarly, if we use excess air, so in this case A is 1.2 times A, so instead of 5 we will have 5 into 1.2 is 6, and this is how the complete combustion expression will look like. So 1 mole of propane reacting with 6 moles of 6 moles of air to give 3 plus 4 moles of water plus 22.56 moles of nitrogen. So similarly, for adiabatic flame temperature, your enthalpy of product will be equal to enthalpy of reactant. So substituting, this is how the expression will look like. We have 3 moles of CO2 plus 4 moles of water, which is same as previous, and now additionally we have 1 mole of oxygen plus 22.56 moles of nitrogen, giving 23,15,950 kilojoule. So here again we start with 2100 Kelvin. So there, if you see, the value is 22,86,690 kilojoule, which is lower, and so we taken next higher value. So taking it at 2150 Kelvin, we get the enthalpy as 23,48,890, which is higher than on the right hand side value. So it, our temperature will lie between 2100 Kelvin and 2150 Kelvin. So doing an interpolation, we get it as 2124 Kelvin or 1851 degree Celsius. So if you see, having this product, excess air has reduced your temperature. So this is what we discussed in the example, in the previous example. Because some of the energy has been utilized in raising the temperature or enthalpy of the oxygen and nitrogen. So that's why your temperature is lower. So I think this is the last problem which I have for today. So we'll see how to solve this. So we have a scenario which is described. So for safe disposal of hazardous waste material in a major environmental concern for industrial societies and creates challenging problem for engineers. So the disposal method commonly used include landfilling, burying in the ground, recycling, or incineration or burning. So this is the types of disposal. So incineration is frequently used as a practical means for the disposal of combustible waste such as organic materials. So the EPA regulation requires that the waste material be burnt almost completely above a specified temperature without polluting the environment. So maintaining the temperature above a certain level, typically about 1100 degrees Celsius, necessitates the use of fuel. When the fuel combustion of the waste material alone is not sufficient to obtain the minimum specified temperature. So what basically they do is, if the waste value of 1100 degrees Celsius, you add extra waste to reach this typical value of 1100 degrees Celsius. So a certain industrial process generates a liquid solution of ethanol and water as the waste product at a rate of 10 kg per second. So they say the mass fraction of ethanol in the solution is 0.2. The solution is to be burnt using methane in the steady flow combustion chamber. So since you using just ethanol, you cannot, you are using methane now as a fuel to combust the solution. So propose a combustion process that will accomplish this task with a minimum amount of methane. So we have mass flow rate of liquid ethanol water solution, which is given as 10 kg per second, and it contains 0.2 mass fraction of ethanol. So the mass of ethanol will be 0.2 times into 100, so 0.2 times into 10, which is the mass flow rate of the solution. So gives you mass of ethanol is 2 kg per second. So your mass of water will be 8 kg per second. And so now we can know since we know mass and molar mass, we can estimate the moles. So the mole of ethanol is mass of ethanol divided by molar mass. So 2 divided by 46 will give you 0.04348 kilomole per second. And similarly, mass of water is mole of water is 8 divided by 18, which gives you 0.444 kilomole per second. So if you find out the ratio, so we get 10.22 moles of liquid water present in the solution for each mole of ethanol. So assuming complete combustion, so the combustion equation for C2H5OH with stoichiometric amount of air is C2H5OH plus AO2 plus 3.76 N2 gives you 2 CO2 plus 3 H2O plus 3.76 A nitrogen. So A is 3. So this is how the expression looks like. C2H5OH plus 3 moles of air to gives 2 moles of CO2 plus 3 moles of water plus 11.28 moles of nitrogen. So here ethanol is in liquid form. So we have with the solution, so we have 1 mole of ethanol reacting with 3 moles of air, and each mole of ethanol will contain 10.22 moles of water in the solution. So 10.22 moles of water to give 2 moles of CO2. So it's same product plus additionally the water. So the heat transfer for this combustion process is determined from the steady flow energy balance equation. So Q is your enthalpy of product minus enthalpy of reactant. So assuming the air and combustion product to be ideal gases, we have so we assume all reactants to enter the combustion chamber at 25 degrees Celsius. So and assume that a reactant is leaving at 1400 Kelvin. So assuming we need 1100 degrees Celsius, so we assume a little bit over, so 1400 Kelvin. So also a rounded value, easier to read in the table. So corresponding 1400 Kelvin. So this is the enthalpy values listed and the enthalpy of formation. So substituting in the expression, so 2 moles of CO2 into enthalpy formation plus the enthalpy difference, and similarly 3 moles of water into enthalpy of formation and the enthalpy differences, and so on, and then 10.22 moles of enthalpy of water which was present into enthalpy of formation plus the enthalpy difference. So minus 10.222 moles into enthalpy of water at liquid state. So this is the enthalpy difference for the liquid. So because it's not getting formed basically from the reactant, it is already present. So this is in gaseous form and this is in liquid form. So that's why we have taken 10.22 of water which was present as a product. So now it is formed at it has been in gas form and at temperature of 1400 Kelvin. So that is the value for enthalpy minus the enthalpy formation as liquid. So that is the total enthalpy change for the water which was present. So we get a Q as 29 lakh 2,95,409 kilojoule per kilomole of ethanol. So that is the Q which is required. So for the given mass flow rate, so the mole of ethanol is 0.04348. So the heat required for this mole is, we multiply the heat for 1 mole divided into the number of moles of ethanol. So 0.04348 into your heat generated per kilomole of ethanol, so gives you 12,844 kilojoule per second. So that is the heat which is required to be generated. So if we assume methane combustion, so this is the expression for complete combustion of methane, which gives you CO2 2 moles of air reacting to form 1 mole of CO2 and 2 moles of water and 7.52 moles of nitrogen. So similarly, applying in first law, Q is again product minus reactant, and reactant coming at 1400 Kelvin. So we get Qs minus 396,790. So we get 3,96,790 kilojoule per kilomole of methane. So the mole of methane which is required will be the heat which is required for ethanol divided by the total heat per kilomole for methane, which will give you Q number of moles of methane required as 0.03237 kilomole of methane. So multiply by molar mass will give you the mass. So mass will be 0.5179 kg per second. So therefore we must supply methane to the combustion chamber at a rate of 0.5179 kg per second in order to maintain the temperature at 1400 Kelvin. So this amount of methane has to supply because the water which was present in the solution, now it is as it takes away some of the heat generated by the methanol and gets converted into vapor. So that will absorb some of the heat. So it cannot maintain the temperature at 1400 degrees Celsius, 1400 Kelvin. So you add combust methane to keep this product at 1400 Kelvin. So that's why we are supplying methane, and we by ensuring that we are supplying this amount of methane, we can maintain this product to be at 1400 Kelvin. So whatever heat is required for the combustion, so if you see there Q, it is in positive quantity, this has to be supplied. Usually we see that Q will be negative, that means the heat has rejected to the surrounding. Here you see heat is in Q is in positive quantity, so this says that you need to supply this much amount of heat for combusting 1 mole of this solution, 11.22 moles of solution. You can consider 1 kilomole of ethanol contains 10.22 kilomoles of water. So this solution, you need to supply this much amount of heat to maintain it at 1400 Kelvin. So that is being supplied by your methane. So that's what this problem says. With that, finished the questions which I prepared for today on combustion, and we saw today the energy balance on the combustion, how much the heating values will be. So heating values we generally calculate using the reactant and product at the standard temperature and pressure. and then adiabatic flame temperature. In that case, you assume that no heat is transferred. So in that case, what will be the product temperature? That will be your adiabatic temperature, flame temperature. So that's how we calculate, and with that the combustion portion has been finished with this week 10, and we'll continue next class. So thank you. We'll see you next class.